Hello, everyone. In this video, we'll be discussing 1.4, Modeling with Linear Functions, the Creating a Model section. When we're talking about modeling with linear functions, we are looking at the world around us and creating a model that can help us predict the future, especially with linear functions. You know, we've studied the slope, the y-intercept, and the 2 points x, y. Those variables can change over time. They vary. And so we can look at the model and plug in x and solve for y, or plug in y and solve for x. So first of all, how do we create this model? We're looking at this situation with carbon dioxide in the atmosphere. And we know as the carbon dioxide increases, the temperature increases also. So it's important for scientists and people who study the weather to understand this idea. We have this graph that we've looked at previously that kind of shows these carbon dioxide levels over time. And so time would be the independent variable on the x-axis because it just keeps ticking independently. And then the amount of CO2 in parts per million would be the y-axis, the dependent variable. Here it asks us to do a few things. So if you look at part A, let's find the average rate of change. So anytime it says rate of change, it talks about the slope. Okay, so let's just refresh that. The slope, it's the rise over the run. Change in y over x. Remember, that's the Greek letter delta. That means change, okay? And when we're talking about change in y over x, we are talking about a rate of change. What does it mean to be a rate? Think about rates in the real world. Dollars per hour, revolutions per minute, miles per hour, miles per gallon. Okay, so when you're talking about rates, you're comparing two units. So for example, hey, how much do you make? Oh, I make this many dollars per hour. Or, how fast were you driving? I was driving this many miles per hour, kilometers per hour, etc. All right. So when we're talking about the rate, when we look at a real world situation, we're trying to find those two variables that are being used. And here we have the amount of CO2 and the years. So notice the amount of CO2 in parts per million. So this is the amount of carbon dioxide and the year. We can look at our units and know which one's the independent variable and which one's the dependent variable. This is always y over x. And so we know that the dependent variable is the carbon dioxide and the independent variable is the years. So once we find the slope, boom, then we have the information that we need to know the x value and the y value. Okay. Here it's saying, let's find that average rate of change from 2008 to 2023. And we need the slope formula. So remember, you subtract the y's over subtracting the x's. That's what this means right here. Change in y, y2 minus y1. All right, we need some information. What is that CO2 level in 2023 and 2008? So if you click on the interactive graph, it'll take you to this graph and let's get our data. If you look over here, it'll show the year. So we're looking at 2008. January of 2008 is 385.78. So let's put that here, 385.78, and that would be in 2008, it's 385.78. That's our ordered pair, the X and the Y. Now let's look at 2023. So January of 2023, 419.47. Okay, now we have the data that we need, 419.47. That would make our ordered pair in 2023, 419.47. Okay, how do I find that rate of change? Well, subtract the y values, but what if you're confused on which one is the y and which one is the x? Well, we already know the slope, right? We already know the slope is CO2 in parts per million over the years, which is time. We already know that this is the change in y over x, which means y is parts per million and x is years. So let that help you. All right. So let's take the change in y. So we'll take 419.47 and subtract 385.78. And then we'll divide that by 2023 minus 2008. Then you get your calculator out. 419.47 minus 385.78. That's 33.69. And then 2023 minus 2008. We're talking about 15 years here. So 33.69 divided by 15. And that means your rate of change is 2.246. The average CO2 increase per year from 2008 to 2023 is 2.246. Now that we found that rate of change or the slope, they're asking us to let X represent the number of years since 2008. So 2008 will be our 0 point. When X is 0, that is the y-intercept. So kind of remember the math nerds' favorite form of the equation of a line is the slope-intercept form. We love this because it gives us really good information. The slope-intercept form of the equation of the line is y equals mx plus b. And so we'll talk a lot in this section about m, the slope, which is what we've discussed here, and b, the y-intercept. B is where you begin, your initial value, maybe a one-time fee or a down payment, just a one-time thing where you begin. And when you're looking at a graph, so when we're looking at a graph, the B is the y-intercept. So whatever situation, I make this many dollars per hour. So I get a new job, they give me a bonus of $100. So I start at $100 and then they're going to pay me $20 an hour. So that line will just keep going. What about miles per hour? We switched drivers. Now I'm driving and that doesn't really work very well because you're not going to zoom right up to 100 miles an hour. So you would start down here, right? I started at 0 miles an hour and then I gradually accelerated. Now I have this constant rate. Okay, so the slope-intercept form and how we can use that. So they're asking us, let Y represent the amount of carbon dioxide in 2008. So here I know that my X value is 0 and my Y value is 385.78. All right, now we have the two pieces that we need to use this information to write that equation in slope-intercept form. So Y equals mx plus b. We begin at 385 and 7.78 parts per million of carbon dioxide, and then every year it'll increase by that 2.246. Now that we have this awesome model, it's our template. We can use this linear template to predict the future. And that's why it's exciting to model that world around us. Find these templates and utilize them. Make predictions and make some good decisions. What are we going to do about this knowledge? All right, so can we predict the amount of CO2 in 2035? So here's where I was talking about they'll either give you the X value or the Y value and ask you to solve for the other. These two pieces of your equation are called variables. The X and the Y vary, they change. And so, how much money did you make? Well, it depends on how long I worked. If you worked for 10 hours, making $20 an hour, then you would get the $200. but you started with the $100 bonus, so your total amount of money is $300. Okay, so let's look at our situation here. Predict the amount of CO2 in 2035. You just have to use your units and plug it into the right spot. I want to know the amount of CO2. That's the Y value, CO2. We can see that here. The Y value is CO2, the X value is the year. So in 2035. Now, my only concern here is, should I just say 35? What do I do with the year? What is my X value? So the X value is whatever year it is, and you subtract your starting point. Remember, we're beginning this scenario in 2008. And so 2035 minus 2008 would give you 27 years. So after 27 years, how much CO2 is in the atmosphere? We can just plug that in. Plug it in, plug it in. So we plug in the 27 years for X. So 27 times 2.246. That's 60.642. And then you add the 385.78. And we see that in the year 2035, we will have 446.422 parts per million of CO2. We can do the same thing for the year 2050. So remember, your X value will be 2050, subtracting that beginning of 2008. So this would be after 42 years. And then we do the same. So 2.246 times that 42 years, adding that starting point of 385.78. So 42 times 2.246, that's 94.332, and then we add the 385.78. You get 480.112 parts per million of the CO2. Make sure you always label your answer when you're talking about the real world. Okay, so I plug in 27 years, and this is the amount of CO2 in the atmosphere. I plug in 42 years, this is the amount of CO2 in the atmosphere. Now, they can ask you the other way. In which year will the amount be 500? So where do I plug this in? If you can see that the Y value, the units is parts per million, the X value, the units is years, then boom, when I see 2035, I know I'm plugging in for the X. When I see parts per million, I know I'm plugging in for the Y. So here you would plug in 500 for Y and 2.246. Now we don't know what year. That's what we're trying to predict. So X and then plus your starting point, 385.78. Now, how do I solve this? Subtract the 385.78 from both sides. So 500 minus 385.78 would give you 114.22. And then you would divide by the 2.246. And this gives you approximately equal to 50.8549. So almost 50 years, 51 years, almost 51 years, but still 50 years. So in which year? So you take 2008 and you add the 50 years, predict which year. So that would be in the year 2058. Now it's almost 51 years, but we're still in that 50th year. So in the year 2058. You don't just say, oh, 50 is my answer. No, you answer the question, predict which year. So then you could say in the year 2058. That's how you create this model from real world situations. Understanding the slope is the rate of change. Understanding the beginning point is that y-intercept, and understanding that you can find ordered pairs, x and y values that vary over the time, and then you can use this model you created to predict the future. You can either plug in the x value of years and solve for the y value of parts per million, or you can plug in the y value of parts per million and solve for the x value of years. Thank you so much. We'll see you next time.